Okay guys, let's take a look at today's lesson. We're going to be looking at particle motion. We're going to spend a couple of days on it. Today, the first thing we're going to do is really talk about all the definitions and make sure we understand some, and there's a few new concepts that we're going to learn. So, we've talked about the position function before. It's typically written as s of x or s of t or x of t. It's a function of time t. It gives the position relative to the origin of an object. So that's the position function. Instantaneous velocity is going to be telling us how fast something is going at an exact instant and in which direction. It gives us two pieces of information about the particle. And it's denoted by v of t, or if we're in terms of f of x, or dy dx. Speed is going to tell us how fast the object is going, no matter which direction. And it is the absolute value of velocity. So speed is the absolute value of velocity. It takes out the direction. Acceleration is the derivative of the velocity with respect to time. And our acceleration, it's usually denoted as a of t, or perhaps one of these other techniques, f double prime, or the d2yx dx squared. The jerk is the derivative of acceleration with respect to time. It is the rate of change of acceleration. Now, I know nobody in here has probably experienced accelerating quickly or anything like that. You've probably seen it on TV maybe, where people like hit the gas and then they're kind of thrown back. This measures that. That's what this measures. Okay? Maybe that's where it got its name from, because people are like, thrown back in the car if you accelerate quickly. Like I said, nobody in here knows that. I mean, just like on TV, when you see it on TV. All right, so let's talk about the behavior. Let's look at this graph and talk about basically the particle is moving forward when the velocity is positive, and it's moving backwards when the velocity is negative. We've kind of talked about that before. I think we've talked about increase, decrease with regular functions. With particle motion, it's moving right or moving left, forward or backward. What we really haven't talked very much about before, or at all actually, is the speeding up and slowing down. So if the signs of the velocity and acceleration are the same, no matter if they're both positive or both negative, their forces working in the same direction, you're going to be speeding up. If they have opposite signs, and it doesn't matter which is which, but if they're opposite, one's positive, one's negative, that's going to cause the particle to slow down. Okay, so that's just something that we need to be aware of. Those are questions that they're going to ask. Is the particle speeding up, slowing down? And we have an example that we're going to work with that. But let's look at what it looks like on this graph. I think it's a pretty good descriptor. This is a graph of the velocity function. And notice here, my velocity, if it's above the x-axis, velocity is positive, below is negative. So let's kind of look at this. How do we read the second derivative off of the first derivative? We look at the slopes, right? The slopes. So we look at the slopes here, and from 0 to 1, my velocity is positive and my acceleration is positive, because this is a positive slope. So therefore, we're speeding up between the times 0 and 1. Here, my velocity is positive, but my acceleration is 0. So we're not speeding up or slowing down. We're remaining constant. There is no acceleration. On this piece right here, between 2 and 3, my velocity is positive, but my acceleration is negative, because these are negative slopes, right? So the signs are different, so we would be slowing down between 2 and 3. Okay, is that making sense? Now, let's look at this case right here when velocity is negative. It's underneath the x-axis. So velocity is negative. Here, my acceleration, the slopes, the signs of these slopes would be negative. So velocity is negative, acceleration is negative. We're speeding up between 3 and 4. Here, we have the opposite effect. My acceleration is positive and my velocity is negative, so we're slowing down. Now let's talk about maximum speed, because this is talking about the greatest speed. Speed is the absolute value of velocity, and I know you've seen absolute value graphs before. You know how everything underneath the x-axis is flipped up? You've seen that before? So if you would think about when we're looking for greatest speed, we are looking for the absolute value of velocity. So if we were to take this and flip it up, I think you would be able to see that this would be the fastest. With me, this velocity would be the greatest. Though we're going backwards, it's still the greatest speed. Okay, so that's just something we need to be aware of. It is possible for speed to occur when velocity is negative. All right, and I think that pretty much covers all the content on this slide. Do we feel okay with that? Okay, let's take a look. We have one example to do. This piece right here, we want to make sure that we see this. We have a particle moving along a horizontal line so that its position at any time where t is greater than 0, gives us a restriction, is given by this position function. Okay? Where s is measured in meters and t in seconds. All right, so let's take a look at part A. It says find the velocity at time t and at t equals 1. Well, find the velocity at time t is a very fancy way of just saying find the equation of velocity. That's what it's asking you to do. So let's do that. So v of t is going to equal 6t squared minus 14t plus 4. So there is our velocity at time t. So now let's take a look at velocity at 1 second. So v of 1 is going to be 6 minus 14 plus 4. And that is negative 4 meters per second. We need to always remember to put our units. Always remember that. Okay. When is the particle at rest? Moving left, moving right, justify. Okay. So what do we need to know to be able to tell if the particle, how it's moving, left or right? We need the signs of the velocity. Right? That's what we need. So we're going to do just what we did, remember when we did increase, decrease with regular functions. We're going to do set the derivative equal to 0, do a sine chart, and take care of all of that. So let's do that. Now, I want to caution you here. I'm going to factor a 2 out because it is easier to factor. But I have seen students factor out a negative 2 before, or something negative, and then divide it off. That is a big problem. Because if you factor out a negative and divide it off, what have you just done to the signs that you're supposed to be checking? You flipped them all. They're all exactly opposite of what they're supposed to be. So if you're going to factor something out, please don't divide it off. Just get in the habit of just leaving it there. Just leave it there instead of trying to divide it off. I don't want you to be in that situation where you've changed all the signs. So our factoring for that is going to be 3t minus 1. And then t minus 2. All right, so our t values, where the velocity is 0, is 1/3 and 2. So let's make a sine chart. Okay, we've had lots of experience with sine charts. Hopefully we remember. We test the signs where we got the numbers from. So they turn out like this. Okay, so let's answer the first question, at rest. How do we know if the particle's at rest? What are we looking for? 0. We're looking for the velocity to be 0. So it's at rest at t equals 1/3 and t equals 2 because, correct, we justify this just like we did with the other stuff, because v of t equals 0. That's all I have to write. It takes like 5 seconds because v of t equals 0. All right, so let's do left. We're moving left when the velocity is negative. So that's from 1/3 to 2 because v of t is less than 0. Right, pretty straightforward, right? We're okay. So let's go right. We're moving right. Now notice we have this bound right here, so really we're starting at 0. We're not allowed to go on the other side because of this. So we're going from 0 to 1/3 and 2. Are we bound on the right side? No, there's no bound there. So we're just going to go to infinity. And that is because v of t is greater than 0. Okay, pretty straightforward. All right, find the acceleration at time t and then at 1. So again, a of t, let's see, that gives us 12t minus 14. And a of 1 is going to be 12 minus 14, or negative 2. And our units are meters per second squared. Okay. Now the displacement and distance, that's new. We really haven't talked about that before. It's pretty important. I think most of us have a really good understanding of the difference between displacement and distance, but I just want to make sure, because there's maybe somebody that hasn't done physics, or I don't know. So if I'm standing in the middle of the board and I walk 2 steps to the right and then I walk 2 steps back, what is my displacement? It's 0. But what's my distance? 4 steps, right? So the difference, that's a huge difference, right? My displacement is 0 because I'm back where I started, and but my distance is not 0. Is it possible for displacement to be negative? Yeah. Couldn't I end up to the left of where I started? Yeah, sure. It could be negative. That's okay. Just so that you know. All right, so what we're going to have to know how to do is to find displacement whether you have the position or velocity. Sometimes you're going to be given the position function, sometimes you're going to be given the velocity. And I'm going to show you both ways. And it's really important that you know how to do both. So let's say we have the position. So we have s of t. If we have the position, we're going to use a formula. It's end minus beginning. End position minus beginning position. That's basically all we do. And in this case, we're going from 0 to 3. So if I have the position, I would do s of 3 minus s of 0. My end position minus my beginning position. And s of 3 is 8. And s of 0 is 5. And so my displacement is 3 meters. Okay, that's it. If you have the position, you simply do end minus beginning. Displacement is pretty straightforward. What if I had velocity? If I had velocity, how would I find displacement? I would integrate it. I would do the integral from 0 to 3 of v of t dt, and I would get 3 meters. I would get the exact same thing. Okay, so it depends on what you have. If you're given position, do end minus beginning. If you're given velocity, do the integral. The integral is displacement. Okay, so I think displacement is really the easiest of the two. Distance is a little bit harder because we have to account for the times that we're going backwards. So we have to know when we're going backwards first is the issue, and then we're going to have to account for it. We can't just do end minus beginning. So if we have the position, now we're asked to find distance. If we have the position, what we're going to have to do is end minus beginning every interval. So if we look up here, here's my sine chart for how we're moving, when we're moving right, when we're moving left. I'm going to have to do end minus beginning for this interval, end minus beginning for this one, and for this one. I'm going to have to do 3 of them because I have a problem here. Here I'm moving backwards and we have to account for it. So if I have the position, I would do s of 1/3 minus s of 0 plus, and the absolute value, I do the absolute value of each one, plus absolute value of s of 2 minus s of 1/3 plus absolute value of, and we're going to 3 here, s of 3 minus s of 2. I find all those function values, I do all that arithmetic, and just for time's sake, I'm not going to go through the arithmetic part right here for time's sake, but that's what you would do. And basically we're going to get 331 over 27. You would certainly have a calculator for a number like that. I wouldn't be asking you to do that in your head. That's approximately 12.259 meters. Okay, so that would be our distance traveled from 0 to 3. Quite different than our displacement. Our displacement was 3. Our distance is 12.259. Now, what if we had velocity? What if we had velocity and we were asked to find distance? What do you think we're going to have to do? Yeah, we're going to have to do 3 integrals if you're doing it by hand. Now, if you're doing it with the calculator, I'll show you a faster way to do it. If you're doing it by hand, you would do 3 integrals, right? These same three intervals. So I would have to go from 0 to 1/3 of v of t dt. Now, this we know is positive. I think this disturbed some students earlier, so I'm just going to put absolute value around it because I was changing it positive, negative, positive, and that was really troubling people. So we would do the absolute value of that, whatever that was, and in this case it's going to be positive, plus the integral from 1/3 to 2 of v of t dt, of course the positive one, the absolute value of it, plus the integral from 2 to 3 of v of t dt, of course absolute value. When we do that, we would get the 331 over 27. Now, if you have your calculator, it's a much easier thing for you. What you would do is so here's if we had a calculator. If you had your calculator, you would do integral of 0 to 3, and you would put the velocity in absolute value. Do y'all know where the absolute value button is on your calculator? You know, math, it's in that. You would do this, and then you wouldn't have to split the integral into 3 pieces. We just can't do this by hand. You can't just say absolute value of that by hand. I mean, that doesn't really make any, we couldn't do that by hand. But in your calculator, this is what you would input, and then you would get distance. Okay? Does that make sense? All right. So the last thing that we're going to look at is speeding up and slowing down. I need to make myself a little bit of room up here. I'm going to write, so we have our, we have our velocity graph already, right here, our sine chart. We need an acceleration sine chart. So let's make so this is velocity. We need acceleration. Okay, so we haven't done that yet. So here was our acceleration. It was 12t minus 14. We would set that equal to 0. And that gives us 7, 6. And then we do our signs for that, which would be like that. All right. So now we're set up. We have our 2 sine charts. So I think the easiest thing to do, what I usually do is just I write the categories for speeding up and slowing down. And then I go through from left to right and determining what each interval is, and I just put it in the proper place. Is it a speeding up or slowing down interval? All right, we know that we have to start at 0 because that was our restriction. So students a lot of times find this difficult because you're having to compare and contrast 2 sine charts at the same time. So I think you'll probably be fine, but again, some students find this challenging. We want to start at 0. We want to go left to right, and I want to go until I hit my first break. Is my first break at 1/3 or 7/6? 1/3. It's the smallest one, right? We're going smallest interval. So from 0, we have analyzed from 0 to 1/3, my acceleration is negative and my velocity is positive. So where does the interval from 0 to 1/3 belong? In the slowing down one. So I'd write it here, 0 to 1/3. Okay, then I go back. So 1/3, where's my next break point? 7/6. So I analyze the charts from 1/3 to 7/6. So from 1/3 to 7/6, my acceleration is negative. And from 1/3 to 7/6, my velocity is negative. So we are speeding up. I'm going to put that here. So speeding up is between 1/3 and 7/6. Is that okay? All right, so I start at 7/6 now. Where's my next break? At 2. So 7/6 to 2, my acceleration is positive. 7/6 to 2, my velocity is negative. So where's that going to go? Slowing down, right? So 7/6 to 2, we're slowing down. The last interval is from 2 to 3. So from 2 to 3, acceleration is positive, or actually 2, are we just doing till 3? Nope, we're doing till infinity. From 2 on, where acceleration is positive, and velocity is positive from 2 on, so that means that goes in speeding up, 2 to infinity. And there's my speeding up and slowing down. Now we need to justify. Okay, justify. How do we know we're speeding up? They're both signs. So we would say v of t and a of t have same signs. That's how we know, right? V of t and a of t have the same signs. How do we know that we're slowing down? They have different signs. So v of t and a of t have different signs. And that's your justification. That's all you need to do. Okay, are we okay?